In this segment, we discuss regularization. Now, let's take a look at this schematic here. This is a very generic sketch. On the horizontal axis, we have model complexity. On the vertical axis, we have model error. And there are two curves. Both curves are concave up. One curve is for generalization, and another curve is for training. So one way of reading the graph is that as we take increments on the horizontal axis, what happens to both of those curves? So as the model complexity increases, we notice that the training loss is always monotonically decreasing relative to increments on the model complexity. The generalization loss is a different story. It decreases also initially with increments in model complexity. It attains a local extremum and then it reverses monotonic behavior. So the generalization loss begins decreasing behavior, it attains a local minimum, and then it switches into increasing behavior relative to model complexity. So as a refresher, underfitting happens when there is not a lot of information that is learned from the model. So usually the model is too simple. Perhaps there are only a handful of features that are under consideration, and this usually translates in values for the weights. The weights correspond to those features having very small values, almost close to zero. So in general, underfitting models, they don't perform well with the training data set, and they're not expected to do well with other data subsets, such as validation or testing data sets. So on the other extreme, we have overfitting, which is a scenario in which the model would learn very well every explicit detail, every little twist and corner of the data points. So when there is overfitting, we would argue that usually there is too much complexity being considered in all the features, and perhaps the features include combinations that are considered complex and nonlinear. So that usually translates in having values for the weights that are associated with the features, values that are not close to zero. They are in fact larger values. So we would also say in general that models that are overfitting perform well, way too well with the training data set, and usually they don't perform well with the testing data or validation data. Regularization is an approach that implements some penalties for certain values of weights. So this is implemented by using a revised cause function or objective function, where there is a term here, the original cause function, which the original program was aimed at minimizing errors. So that would be considered the original cause function or original error function. And this is still a function of the weights. And there is an additional function that is called the penalty function, which involves a parameter alpha. Here, this parameter is called penalty parameter. The idea is that together, this new revised regularization function, together they are including the minimization of the original error function, and also the minimization of the complexity of the model. So this term that has the alpha coefficient or alpha scalar is taking into consideration minimizing the complexity of the model. So if alpha is 0, that means there is no penalty for any complexity that is applied in the model. If alpha is too large, that means the complexity, the penalty in the complexity is very strong, leading to perhaps models that are underfitting or they are too simple. And what we would like to we would like to think of alpha as perhaps a hyperparameter. So in closing, there are at least mentioned here two types of penalty functions. One of them is called rich. They're also called L2 and L1. This is more of a definition of L2 norm and L1 norm. One of them is still a sum of squares. The other one is a sum of absolute values relative of in relation to the weights. And so there is the L2 regularization, which is also known as rich, and the L1 regularization, also known as the least absolute shrinkage and selection operator, also known as lasso. sklearn has methods for both linear regression and logistic regression. Both the rich and lasso functions are available for regularization in sklearn, and their linear regression and also under logistic regression.